So what we're going to do for this question, we're going to start just writing it out more in the form that we're used to. So again, this is written sort of like a parametric equation. Can you see that this here would be your x? Because that's what the vector I stands for. And this will be your y, and that's your z. So if I was going to rewrite these lines, I could write RL. Well, it has the point 5, 3, and 0 plus S, and the direction is -4, 1, and 2. And RM has -3, 7, and 6 plus T, and its direction is -4, -1. And what am I going to put for this last part of my direction? 0. So it makes sense that no matter what you put in for T, that the value in front of the K will always be 6. Now they have a point in common, and we have to find that point. Wouldn't it have been nice if the point that was the starting point was the same, and then you could just say, well, they both have the same starting point, so that's the point in common, and then they just go off in different directions? But now what we're asking in this question is you're imagining one vector in 3 dimensions, and then you're imagining another vector in 3 dimensions, and in 3 dimensions it could be very possible that they don't cross at all. But we're saying that they do cross at one point, and we're trying to find out what that one point is. Does it make sense if they do cross in a point that their x-coordinate is going to be the same, the y-coordinate is going to be the same at that point, and the z-coordinate is going to be the same? So if we think about our parametric equations for both of these, this one's x-coordinate is 5 minus 4s, while this one's x-coordinate is -3 minus 4t. This one's y-coordinate is 3 plus s, and this one's y-coordinate is 7 minus t. And finally, this one has a z-coordinate of 0 plus 2s, and this one has a z-coordinate of 6. The z would have to be 3. Yes. Oh yeah, the s would have to be 3. So this one, if that's going to work, if they are going to cross, and the way the question is worded is it says they do cross, okay, then according to this last one, s has to be 3. Now if s is 3, if we just move up to this one, if s is equal to 3, then y is equal to 6, right? On the equation on the left. But if y is equal to 6, then what does t have to be? T has to be 1. Does it work? If s is 3 on this side, you're going to get your x-coordinate as -7, right? And if t is 1 on this side, you're going to get your x-coordinate as -7. It works. So the point, the x-coordinate is -7, the y-coordinate is 6, and the z-coordinate is 6. This one was nice because that last one allowed us to just say s has to be 3. What would you do if this last one had a t in it as well? You can make these two equal to one another, but then you'd have, let's say, just even at this point here, do you agree that 3 plus s equals 7 minus t? So we couldn't solve it there. It could be anything with just that one equation, because we have two variables in one equation. But what does that remind you of? Systems of equations. And so had you put both of these together, these first two lines would give you two equations with two unknowns, and you could use substitution or elimination and solve. Just so happened this one was nice, that you could get s equals 3 right away. And then you could find the point. Now we have a point that they intersect. Now that you've found the point where they intersect, we can figure out what the angle is between these two lines. Did we give that point a label? We'll call it point P. So let's draw a picture. We've got line M, line L in 3 dimensions, intersecting at the point P. And we want to find the angle between them. So we go to one of our most important findings, which was our cos theta formula. Cos of theta is equal to, now on your formula sheet you had u dot v over the length of u times the length of v. Did I remember it correctly? Excellent. The absolute value bars represent length. So this is going to be my vector u, and this is going to be my vector v. Because if we look back, it said when two vectors are arranged tail to tail, you can find the angle between them this way. So first of all, we're going to have to figure out what our vector u is and what our vector L is. We know that this is the point P on there. How do we figure out what the vector u is and what the vector L is? Any ideas? Pause it. Okay. So here's our vector equation for L, and here's our vector equation for M. And our u and our v are going to be coming from this equation. And our u is the direction vector for L. And our v is the direction vector. Because if you think about the line L, this is the direction it's going in. The first one is just a position vector of a point on that line. But if you want to actually use the vector going in that direction, this is going to be your u, and this is going to be your v. So, cos of theta equals, remember how to do the dot product. The dot product will be negative 4 times negative 4 would be 16. 1 times negative 1 plus a negative 1. 2 times 0 plus 0. The length of u, a squared plus b squared plus c squared, 16 plus 1 plus 4, root 21. And 16 plus 1 plus 0, root 17.